All right, Physics 2, welcome back. This is part 1 of Thursday's lecture, week 13. So we're going to be moving on with Gauss's law, this time talking about a solid sphere of charge, this time made out of an insulating material. So we've looked at a shell of charge, we've looked at a solid sphere of charge made out of a conductor, both very straightforward, things we've easily calculated using Coulomb's law, and now we're going to look at the electric charge Q distributed through an insulating sphere. So in this case, we have an electric charge of Q. It's distributed throughout an insulating sphere of radius r0. So we're going to calculate the electric field on the outside and on the inside. So on the outside, we're looking at r is greater than r0. So this would be this red Gaussian surface right here. So we can see here is R1, and then we're going to look at this Gaussian surface inside with R2, so that's going to be surface area, or the area A2, and then outside we have the area A1. The Q is uniformly distributed throughout. Okay, so to do the calculations outside, we know that E depends only on R, and we want to go after Q enclosed. So we just use Gauss's law. So we have the surface integral, E dot dA, is equal to E times 4 pi R1 squared, so that's the surface area of a sphere, is equal to Q over epsilon naught, which is the charge enclosed over the permittivity of free space. And this just becomes E equals 1 over 4 pi epsilon naught, Q over R1 squared. This is spherically symmetric. It's easy. We had uniformity of electric field, all perpendicular to the surface. Beautiful. We've seen this before. Boring. Let's move on. All right, so now let's look at approaching this from the inside. So inside the sphere. All right, so R2 is less than R0. So now we're looking at A2. So that is this orange Gaussian surface right here. All right, so we can still take advantage of the symmetry of the sphere. So we know E is the same at all points. And then we know, even with this small area here, so there is definitely some Q. It's not the, I'm going to call this little q. So we know there's some little q inside. And we know that E is going to be perpendicular to the surface at all points. Beauty of choosing a sphere. Okay, so setting up Gauss's law, E dot dA is equal to E 4 pi R squared, so this time it's R2. And we're not done yet, because we actually don't know how to relate this to Q enclosed. So we're given a total charge of capital Q, but we have not enclosed all of capital Q. So if we go back to our original picture, all of capital Q is everything inside of the blue, and we're only looking at a fraction of what's inside of the blue. So, all right, so let's figure out how to go after Q enclosed. So to do this, we need charge density. So rho E to get Q enclosed in A2. All right, so very straightforward to calculate. So rho E is dq dV, or delta Q, delta V. Either is a fine way of thinking about it. Either way, you're still looking at charge per unit volume. And it was given in the problem that it has a uniform charge distribution, therefore the density of charge is constant. So let's go after Q enclosed. All right, so Q enclosed, you're going to have 4/3 pi R2 cubed rho e over 4/3 pi r0, the radius of the sphere, cubed rho e, times the charge. So this is the charge of our section. This is the volume of our section. This is the volume of the total sphere. This is the total charge that we want to scale. So we've got R2 cubed over R0 times Q. So we can see this has canceled, this is canceled, and this is canceled. All right, so combining this with Gauss's law, there it is. So now we can go after Q enclosed. So we have E times 4 pi R squared is equal to Q enclosed over epsilon naught is equal to R2 cubed over R0 cubed Q over epsilon naught, giving us E is equal to 1 over 4 pi epsilon naught Q over R0 cubed times R. All right, so moving on. We're starting to see just how powerful Gauss's law is. Well, actually, I think you've already got there. So we can see all the fun we can have with it and just how beautiful it is in terms of its applications. So let's look at a long uniform line of charge. So we have a very long straight wire possesses a uniform positive charge per unit length lambda. We want to calculate the electric field at points near and outside there and far from the ends. All right, so once again, we have a symmetrical situation. This time it's cylindrically symmetrical. So we have symmetry, and we're dealing with specifically cylindrical symmetry. All right, so essentially, if we draw our long line of charge, here it is. And now we're going to draw our Gaussian surface. So it's going to have length L, and it's going to have some radius R, and we're going to have the electric field. All right, so E is perpendicular to the surface at all points. And there is no flux on the ends. So you have cosine of 90 degrees, which is equal to 0. Okay, so let's do Gauss's law. So we have the surface integral of E dot dA is equal to E times 2 pi RL, which is our length here, is equal to Q enclosed over epsilon naught, which is equal to, we know that it has uniform positive charge per unit length lambda. So let's go ahead and we can sub that in for Q enclosed. We have lambda L over epsilon naught, and we get E is equal to 1 over 2 pi epsilon naught times lambda over R, solving for E. All right, so these are the games that you play with Gauss's law. Now, Gauss's law can be used to determine some really interesting properties of metals that we can take advantage of. So, let's consider a piece of metal polarized by external charges. In equilibrium. All right, so let's just, here it is. So we've polarized it, positives on one end, negatives on the other. Okay, so we might assume that perhaps there could be some interior charge, and then to go after this, we could draw a little Gaussian surface. Is there charge inside here? So this is a Gaussian surface. And we don't know if there's any charge enclosed. So let's find out. So inside the conductor, E is 0. Otherwise, it would not be polarized. And we did that proof earlier. Since E is 0, Gauss's law implies charge inside is 0. So the charge inside our little surface is 0. So if E is 0, then Q is 0. If Q is 0, then E is 0. And this, while perhaps you could use Coulomb's law to go after this, is actually better explained by using Gauss's law. All right, so now let's look at a case where we have a conductor with a hole inside. All right, so it's polarized, a conductor, and there's a hole. There's a hole in the bottom of the conductor. We're going to surround it with a Gaussian surface. Is there charge? Is there charge? We're going to use Gauss's law to find out. All right, can there be charge in there? All right, so once again, we don't know. The Gaussian surface of a metal in equilibrium has an electric field of 0 inside, and it has electric flux of 0 and Q enclosed of 0. But what about the hole? And what we can see is that we get E net is equal to 0, even with charges, as long as Q total is equal to 0. So if you were to draw different Gaussian surfaces, what you would see is that even if there are some charges here, you're going to get 0 very, very quickly. Or is that any charges that are on this area are going to cancel out with the other charges around that, giving you 0. So we could draw another picture. And let's say that there's some positive and some negative. We could do perhaps A, B, C, D, and take different paths going around. And what we'd see is no matter what path we would take, we're still going to pass through the metal where E is equal to 0. And therefore, the potential, oh, you need to see this. The potential difference is 0, and therefore there are no charges on the surface of the hole. Metal in equilibrium has E equals 0 and flux equals 0, as do any holes you make. And this has some very useful real-world applications. So this brings me to the concept called screening. So often you'll surround little boxes with metal, and that's to screen out basically signal. And what we see from this is that you can use a mesh, because a mesh is just a metal with a bunch of holes in it, and that will work just as well as a solid metal. So there you go. And so what will result is you're going to get a net field of 0 in whatever you enclose with this conducting material, even if you're enclosing it with a mesh. All right, so moving on to Gauss's law applied to circuits. All right, so let's take charges out of equilibrium and get them to flow. So what about flowing charges? All right, so if you have flowing charges, so let's looking at a wire segment. And we know that the electric field is going to look like this. So this is our Gaussian surface. Here is our wire with its gradient. All right, so we want to look at Gauss's law to determine the flux on the wire. So at the sides, here and here, at the sides, E is parallel to the surface. And therefore flux is 0. Now, what you can see here is the right end would have flux EA right here, but the left end has flux minus EA. Therefore, the total flux is equal to right side plus left side plus top plus bottom. So this is equal to 0. This is equal to 0. This is positive EA. This is negative EA. Therefore, flux is equal to 0 inside a wire. So that means that there's no excess charge anywhere in the wire, which is exactly what we stated in chapter 18. So no excess charge inside the wire, as expected, this time with using Gauss's law. Now, moving on, let's look at charge at the interface of two wires made out of two different materials. All right, so oops.